name is Yeganeh, and I'm going to present a part of my research on workability of asphalt mixture and the development of an advanced analogical modeling. This work was a part of my PhD, which I defended in July 2024 and was under supervision of Professor Ezio Santagata and Professor Davide Dalmazzo. In this presentation, after a short introduction on workability and its evaluation methods, I will explain the laboratory activities. Then I will focus on the proposed analogical model and its parameters. As a general definition, workability is a measure of how a mixture can be manipulated and shaped into the desired form. It describes the ease of movement of mixture through construction machineries to reach the roadway. Although the concept of workability primarily have meaning while the material is uncompacted, it affects the long-term performance of the pavement. Mixture with lower workability can pose challenges in constructing a smooth pavement and may lead to low compaction issues, resulting in increased air voids and future distresses, which consequently decrease pavement lifespan. The importance of workability arises also when we are dealing with limited space for construction machineries, like when we need to pave a narrow trench or a pothole. Going through the literature about workability, lack of widely accepted method for the measurements or standard or code and also specific equipment was observed. Moreover, several definitions are provided by different researchers in literature, which makes confusions in some cases and are mixed with other concepts like flowability and compactability. In our work, we defined workability as a process that occurs in the field starting from loose condition, means immediately after extrusion from the paver screed, until compaction induced by initial passes of the rollers, while in our work, compactability describes the overall densification potential of an asphalt mixture, which may not reach in the field and includes post-construction traffic-induced densification. Regarding the history of workability evaluation, two major methods are found in the literature. The direct evaluation, in which several conceptual devices were proposed by researchers in their laboratory, and mostly they try to correlate the required torque for mixing the loose mix to its workability. While in indirect methods, these are built upon the compaction behavior of mixture and the compaction curve derived from SUPERVISOR gyratory compactor. For example, in a basic model which is fitted to the semi-logarithmic compaction curve, we can see the slope of the curve, the K, is correlated in some researchers to the workability, while, for example, in the EN standard, it is correlated to the compactability of the mixture. Another well-known study was done by Bahia and his colleagues in 1998, in which they used different terms. They used construction densification index and traffic densification index instead of workability and compactability, and they defined the area under the curve as the energy required for the compaction based on two limits they considered for this calculation. In another study by Margaritis, they used the Moutier model and they found the compaction inflection point. They considered the slope and the number of gyrations to reach this point as two parameters which can be correlated to the workability. In our experimental plan, we considered a systematic variation in the components and conditions that may affect the compaction of the mixture. For example, we considered two different binders, neat and polymer modified. We considered different binder contents, different aggregate skeletons, and different compaction temperatures, different compaction pressures, and also in some cases we considered the use of compaction agents to make different asphalt mixtures. All the mixtures were produced by a manual method, and we used 200 number of gyration for the compaction, and all of them are made in the mold with the size of 100 millimeters. We introduced a model, an analogical model which has newly defined elements. In our model, we have a densifier which is similar to spring, but it is working only in one direction. So, and in its equation is independent of the force. Also, our delayer, which is very similar to the dashpot, has the difference in terms of independence to the force, and also in its equation we use the number of gyration instead of time to be adjusted more for the compaction purpose. The combination of these two elements, when we are setting them in parallel, gave us the DD element, the densifier delayer element, because we call it DD element. And when we are looking to the model, we use the two of these DD elements with one isolated densifier in a series, and we found it very practical for the fitting to the compaction curve. In this For the equation of this model, the single densifier has the compaction compliance, which is equal to the initial compaction, while the DD element is defined based on the compaction compliance of the densifier, and also the compliance of the delayer, which is defined by the NDDI. This NDDI is the number of gyration to reach the maximum of the compaction in our DD element. The sum of the three will give us the total compaction, and if we want to look at the equation, we can see the final equation has been multiplied in 4.6 in the exponential part, which is because we were looking to the 99.99% compaction in our DD elements. These diagrams are showing the densification happening in each of the elements. The single densifier has a constant from the beginning to the end, but the other two are increasing to a certain point and then they're reaching their plateau value. This certain point is the NDDI. And the sum of the three will give us the final compaction curve, which is more visible in the other slide. You can see it is perfectly fitted to the experimental data, and based on this model and the element of this model, we define two new indices for workability and compactability. The workability is defined as the compaction reached at the NDD1, while the compactability is the complete potential compaction of the model, which is equal to the summation of the three compaction compliances. For the fitting purpose, we try to collect data from both the experimental campaign we had with the varied elements, and also we collect compaction data from other projects. In total, we have 20 different mixtures which are varied in the binder content, aggregate skeleton, and compaction temperature. And also we have other similar compaction data from different projects, which we try to correlate the result of the indices we propose to the indices found in the literature. As you can see, the binder content, the variation in binder content here, increasing in binder content always increase the initial compaction, means D0. The quasar aggregate skeleton shows lower initial compaction, and also finer aggregates reach the full capacity of densifier at lower number of gyration, which means NDDI is lower. When we are checking the compaction temperature, again we can see higher compaction temperature gave us higher initial compaction, the D0, and the other parameters are affected by this. So when we are comparing our indices to the one introduced in the literature, we can find the correlation, a very good correlation between our indices and those introduced by Bahia and his colleagues. As the conclusion, I can say the model we developed in this study has an acceptable fit to the experimental data and compaction curves, and it is adequate for interpretation of the densification process of different mixtures. The systematic assessment and correlation between mixing conditions shows the sensitivity of each element within the model, and the comparison between indices found in literature and our indices shows an acceptable correlation, especially with those are based on energy. Thank you for listening.